There is an assumption so basic that we rarely notice it. When you look away from an object, it continues to exist in the same state, with the same properties, whether you observe it or not. A chair remains in its position. A coin shows heads or tails. The moon orbits even when no one watches. In 2022, 3 physicists received the Nobel Prize for proving this assumption false. Their experiments demonstrated that certain pairs of particles do not possess definite properties until measured, and that measuring one instantly determines the state of the other, regardless of distance. The universe, it turns out, does not consist of separate objects with independent realities. It operates by rules we still struggle to accept, rules that suggest reality itself may be relational rather than absolute. This discovery did not arrive suddenly. It emerged slowly over decades through a chain of insights that began with a thought experiment and ended with light. For most of human history, the world appeared to operate by principles we could understand through observation and reason. Objects existed in space. They had definite locations, definite speeds, definite properties. A rock falling from a cliff followed a predictable arc. A planet moved along an orbit that could be calculated centuries in advance. The universe seemed to be a vast mechanism, intricate but ultimately knowable, governed by laws that did not depend on whether anyone was watching. This was the foundation of classical physics, the framework built by Newton and refined by generations of scientists who measured, predicted, and confirmed that nature behaved consistently. The elegance of this worldview lay not just in its accuracy, but in its intuitive coherence. Cause preceded effect. Forces acted locally, through direct contact or fields that propagated at finite speeds. An object here could not instantly affect an object there without something traveling between them. The universe was made of separate things, interacting according to rules, and those rules were the same everywhere. This understanding was not merely theoretical. It was woven into the fabric of human perception. When you push a door, it opens because your hand exerts force on the wood. When you see the sun, you are observing light that traveled from its surface to your eyes across empty space, carrying information at a fixed speed. The world felt solid because solidity was a reliable concept. A table existed as a table whether you were in the room or not. Its atoms held their positions. Its molecules vibrated in patterns determined by temperature and pressure. If you measured the table's dimensions at one moment and returned hours later, those dimensions would be unchanged unless something physically acted upon it. This was locality, the idea that objects possess properties independent of observation and that influences propagate through space in a continuous, traceable manner. It was also determinism, the notion that if you knew the precise state of a system at one moment, you could, in principle, calculate its state at any future moment. The universe did not roll dice. It followed equations. Even as physics evolved, this intuition remained intact for centuries. Maxwell's equations unified electricity and magnetism, showing that light itself was an electromagnetic wave rippling through space. Einstein's relativity reshaped our understanding of time and gravity, revealing that space could curve and clocks could run at different rates depending on motion and mass. But these discoveries, profound as they were, did not challenge the essential picture of a universe made of definite things in definite states. Relativity preserved locality. It insisted that no signal, no influence, could travel faster than light. The speed of light became a cosmic limit, a boundary that protected the structure of cause and effect. If something happened here, its consequences could only reach there after enough time had passed for light to cover the distance. The universe remained a place where events unfolded in an orderly chain, where knowing the present meant you could predict the future, where reality existed independently of observation. This framework was not just intellectually satisfying, it was deeply comforting. It suggested that the universe, however vast and complex, was fundamentally comprehensible. Human beings, equipped with mathematics and careful measurement, could decode its workings. The same laws that governed falling apples also governed the motion of galaxies. There was a unity to existence, a coherence that transcended scale. And because objects had definite properties, whether observed or not, science could be objective. A measurement revealed what was already there. The act of looking did not create reality, it merely uncovered it. This distinction seemed obvious. A thermometer placed in a cup of water does not create the water's temperature. It registers a value that existed before the measurement began. The universe, in this view, was like a vast landscape that existed fully formed, waiting to be explored. Scientists were cartographers, mapping terrain that was already present, already real. But in the early 20th century, something began to fracture this picture. It started quietly, with anomalies that seemed minor at first. Certain phenomena involving light and atoms did not behave as expected. When physicists examined the behavior of very small things, electrons, photons, the constituents of matter itself, they encountered patterns that classical physics could not explain. These were not mere measurement errors or gaps in understanding that could be filled with better instruments. They were indications that the rules governing the microscopic world were fundamentally different from the rules governing everyday experience. The mathematics that described these small-scale phenomena worked with astonishing precision, predicting experimental outcomes to many decimal places. But the implications of that mathematics were deeply strange. They suggested that particles did not have definite positions until measured, that light could behave as both wave and particle, that the act of observation seemed to play a role in determining what was observed. The classical picture, so elegant and intuitive, began to show cracks that would eventually widen into something far more unsettling. The first clear sign that something was wrong appeared in experiments with light. When a beam of light passed through two narrow slits and struck a screen behind them, it did not produce two bright bands as you might expect from particles traveling in straight lines. Instead, it created a pattern of alternating light and dark stripes, an interference pattern characteristic of waves. This made sense if light was a wave, with crests and troughs overlapping and cancelling each other out in predictable ways. But light also behaved like particles in other experiments, arriving at detectors in discrete packets of energy called photons. So physicists faced a puzzle. Light seemed to be both wave and particle, depending on how you looked at it. This duality was strange, but perhaps it could be accommodated. Perhaps light was simply more complex than classical physics assumed, possessing both wave-like and particle-like aspects that manifested under different conditions. The strangeness deepened when experimenters tried to observe which slit each photon passed through. If you set up detectors at the slits to record the path of individual photons, the interference pattern disappeared. The wave-like behavior vanished the moment you tried to determine which route the photon took. In its place appeared exactly what you would expect from particles, two bright bands on the screen, one behind each slit, with no interference. The act of measurement seemed to change the outcome, not because the detectors physically disturbed the photons in some crude mechanical way, but because observing the path itself altered the nature of what was observed. When unobserved, photons behaved as if they passed through both slits simultaneously, interfering with themselves. When observed, they behaved as individual particles taking one path or the other. The universe appeared to respond to whether it was being watched. This was not a problem with the equipment or the precision of measurement. The effect persisted no matter how carefully the experiments were designed. It appeared not just with light, but with electrons, atoms, even molecules. Any quantum object, when sent through a double-slit apparatus, produced interference patterns that vanished upon observation of the path. The phenomenon suggested that particles did not have definite trajectories until measured. Before measurement, they existed in a state of superposition, a mathematical description in which they were, in some sense, traveling along all possible paths simultaneously. Only when a measurement occurred did this wave of possibilities collapse into a single definite outcome. The mathematics of quantum mechanics described this process with extraordinary accuracy, but offered no clear picture of what was actually happening. It provided probabilities, not certainties. It told you what you would find when you measured, but remained silent about what existed before the measurement. Werner Heisenberg formalized another aspect of this strangeness in his uncertainty principle. It stated that certain pairs of properties, such as position and momentum, could not both be known with perfect precision simultaneously. The more accurately you determined where a particle was located, the less accurately you could know its speed, and vice versa. This was not a limitation of measurement technology, it was a fundamental feature of reality itself. The particle did not possess both a precise position and a precise momentum at the same time. These properties were inherently indefinite until measured, and measuring one made the other more uncertain. The universe, at its smallest scales, was not made of objects with well-defined states. It was made of potentialities, probability clouds, states that defied classical description. The implications were disorienting. In the classical world, you could imagine a particle as a tiny billiard ball with a definite location and velocity at every moment, even if you did not know those values. Quantum mechanics rejected this picture entirely. It said that asking where an electron is when you are not measuring it is a meaningless question, like asking what color a sound is. The electron does not have a position in the classical sense until position is measured. Before that moment, it exists in a superposition of many possible positions, described by a mathematical function called a wave function. This wave function evolves smoothly according to precise equations, spreading and interfering in ways that can be calculated exactly. But when a measurement occurs, the wave function collapses, and one specific outcome is realized from the spectrum of possibilities. The process of collapse was abrupt, discontinuous, and seemed to involve the observer in a way that made physicists deeply uncomfortable. Niels Bohr, one of the architects of quantum theory, argued that this was simply how nature worked at small scales. He developed the Copenhagen interpretation, which held that quantum mechanics was a complete description of reality, and that it made no sense to ask what a particle was doing when unobserved. The wave function represented everything that could be known, and observation brought a definite reality into being from a field of potentials. This interpretation avoided metaphysical speculation by refusing to describe an unobserved reality. It worked, in the sense that it allowed physicists to make predictions and design technologies, but it left many questions unanswered. If measurement causes collapse, what counts as a measurement? Does it require a conscious observer, or is any interaction sufficient? Where is the boundary between the quantum world of probabilities and the classical world of definite outcomes? These questions lingered unresolved as physicists applied quantum mechanics with increasing success to atoms, molecules, and eventually the technologies that would define the modern world. Einstein found this picture unacceptable. He believed that the universe had to be made of real objects with definite properties, whether observed or not. The idea that observation created reality seemed to him a surrender to mysticism, a failure to find the deeper deterministic theory that must underlie the probabilistic surface of quantum mechanics. He famously remarked that God does not play dice, expressing his conviction that the randomness in quantum predictions was not fundamental, but a sign of incomplete knowledge. Somewhere beneath the probabilities, he believed, there had to be hidden variables, unobserved factors that determined outcomes in advance, preserving the classical picture of a universe that existed independently of observation. In 1935, Einstein collaborated with two colleagues, Boris Podolsky and Nathan Rosen, to formalize his discomfort in a thought experiment that became known as the EPR paradox, named for their initials. They described a situation involving two particles that had interacted and then separated, moving far apart in space. Quantum mechanics predicted that these particles would remain correlated in a peculiar way. If you measured a property of one particle, such as its spin along a particular axis, the measurement would instantaneously determine the corresponding property of the other particle, even if the two were now separated by vast distances. The particles were said to be entangled, bound together by a relationship that persisted regardless of separation. Einstein and his colleagues argued that this correlation had to be explained by something the particles carried with them when they separated, some hidden information encoded in their states that predetermined what any measurement would reveal. The alternative, that measuring one particle instantly affected the other across empty space, violated the principle of locality. It suggested that information could travel faster than light, or that the universe was fundamentally non-local, with distant parts somehow connected in ways that defied the structure of space-time. Einstein called this spooky action at a distance, a phrase that captured his deep unease with the idea. He was not merely being poetic. The phrase expressed a serious objection rooted in the principles of relativity. If measuring a particle here could instantly change the state of a particle there, it implied a kind of instantaneous influence that relativity forbade. Relativity insisted that no signal, no causal influence, could propagate faster than light. This was not just a speed limit for physical objects, it was a fundamental constraint on the structure of cause and effect. If something happening now could affect something light years away without any time delay, it would allow for causal paradoxes, situations where an effect could precede its cause, depending on the observer's frame of reference. The consistency of relativity depended on locality, on the idea that influences propagated at or below the speed of light. Quantum entanglement seemed to threaten this consistency, suggesting either that quantum mechanics was incomplete or that the universe was far stranger than even relativity had revealed. The EPR argument was clear and logical. Either quantum mechanics failed to provide a complete description of reality, meaning hidden variables existed that quantum theory did not account for, or the theory implied non-local influences that contradicted relativity. Einstein believed the first option was the only reasonable conclusion. Particles, he argued, must carry hidden information that determined in advance what measurements would find. When you measured the spin of one entangled particle and found it pointing up, the other particle's spin was already pointing down before you measured it, because both particles had carried this information with them since they separated. The correlation was real, but it was not mysterious. It was no stranger than a pair of gloves separated and placed in different boxes. If you opened one box and found a left glove, you would instantly know the other box contained a right glove, not because opening one box affected the other, but because the correlation was established when the gloves were separated. The apparent mystery of entanglement in this view was merely a reflection of quantum mechanics' failure to describe the underlying deterministic reality. Bohr and others who defended quantum mechanics responded that Einstein was imposing classical assumptions on a non-classical world. They argued that entangled particles did not possess definite properties before measurement. The correlation was not pre-existing information, but something more fundamental, a quantum relationship that could not be reduced to classical hidden variables. The particles were not like separated gloves with predetermined identities. They were genuinely indefinite until measured, and the measurement of one somehow brought both into definite states simultaneously. This was not a signal traveling between them. It was a feature of quantum mechanics itself, a kind of correlation that had no classical analog. Bohr maintained that locality was preserved because no information could be transmitted using entanglement. You could not control what outcome your measurement would produce, so you could not send a message by measuring entangled particles. The correlation was real, but it could only be detected by comparing measurements after the fact, and that comparison required classical communication at or below the speed of light. For decades, the argument remained philosophical. Both sides could claim consistency with the known facts. Quantum mechanics made correct predictions, but it did so using mathematics that was deeply counterintuitive. Hidden variable theories could, in principle, reproduce those predictions by postulating unobserved mechanisms beneath the quantum description. There seemed to be no way to decide between these interpretations experimentally. The debate was a matter of taste, of which assumptions you were willing to accept. Some physicists found the Copenhagen interpretation pragmatic and chose to focus on using quantum mechanics rather than interpreting it. Others felt, like Einstein, that a deeper theory must exist, one that restored determinism and locality. The universe could not truly be probabilistic at its core. The randomness had to be apparent, a consequence of ignorance rather than fundamental indeterminacy. The question hung in the air for nearly 3 decades, unresolved and perhaps unresolvable, a dispute about the nature of reality that seemed destined to remain a matter of philosophical preference rather than empirical fact. But in 1964, a physicist named John Bell discovered something unexpected. He found a way to turn the question into an experiment. He derived an inequality, a mathematical relationship that any local hidden variable theory would have to satisfy. And he showed that quantum mechanics predicted violations of this inequality under certain conditions. If experiments could be performed with sufficient precision, they would reveal whether the universe obeyed Bell's inequality or violated it, whether reality was local and deterministic or something fundamentally different. Bell's insight was both simple and profound. He recognized that if particles carried hidden information that predetermined measurement outcomes, this would place mathematical limits on how strongly the particles could be correlated. The reasoning was subtle but accessible. Imagine that two entangled particles separate and travel to distant locations, where observers measure their properties along various axes. If each particle carries hidden variables that determine what every possible measurement would reveal, then the particle is like a set of instructions, a list of answers to questions that might be asked. When you measure along a particular axis, you are reading one answer from this pre-existing list. The correlation between the two particles arises because they carry complementary instructions, prepared when they were created together. This is the local hidden variable picture. Local because each particle carries its own information independently, hidden because we cannot observe these variables directly, only their consequences when we perform measurements. Bell showed that this picture imposed constraints. If correlations arose from pre-existing instructions carried separately by each particle, then there were limits to how strong those correlations could be for certain combinations of measurements. He derived an inequality that any local hidden variable theory had to obey. The mathematics involved probabilities and averages, comparing the results of measurements along different axes. The details were technical, but the essence was clear. Local realism predicted that certain statistical patterns would fall within specific bounds. These bounds were not arbitrary. They followed necessarily from the assumptions that particles possessed definite properties independent of measurement, and that influences could not travel faster than light. Quantum mechanics, however, predicted violations of Bell's inequality. For certain configurations of entangled particles and certain choices of measurement angles, the quantum predictions fell outside the bounds that local hidden variables allowed. The difference was not subtle or ambiguous. Quantum mechanics predicted correlations stronger than any local theory could produce. This was extraordinary. It meant that the debate between Einstein and Bohr was not merely philosophical. It could be resolved experimentally. If you created entangled particles, separated them, and measured their properties along carefully chosen axes, the strength of the correlations would tell you whether the universe was locally real or fundamentally quantum. If the correlations obeyed Bell's inequality, Einstein was right and quantum mechanics was incomplete, requiring hidden variables to fill the gaps. If the correlations violated the inequality, Bohr was right in a way even he might not have fully anticipated. Reality itself was non-local, and particles did not possess independent predetermined properties. Bell's theorem transformed the question from metaphysics into physics. It provided a concrete, testable prediction that distinguished between worldviews. The theorem did not favor one outcome over the other in advance. It simply said, nature will reveal which framework is correct if you perform the right experiments. The beauty of the theorem lay in its generality. It did not depend on the specific details of any particular hidden variable theory. It applied to any theory that satisfied the assumptions of locality and realism. Locality meant that measuring one particle could not instantly affect the other. Realism meant that particles had definite properties before measurement. These seemed like modest, reasonable assumptions, the kind that any sensible description of reality should satisfy. Bell showed that together they led to an inequality that nature could either obey or violate, and that quantum mechanics predicted violation. The theorem was published in 1964, but it took years for the physics community to fully appreciate its significance. Bell was not working at a major research institution when he developed his ideas. He was at CERN, the European Particle Physics Laboratory, and his work on the foundations of quantum mechanics was something he pursued outside his main responsibilities. The theorem appeared in an obscure journal and initially attracted little attention. Quantum mechanics was already well established as a practical tool, used daily in laboratories around the world to predict outcomes with astonishing accuracy. Most physicists had made peace with its strangeness, accepting the Copenhagen interpretation, or simply ignoring foundational questions to focus on applications. The idea that these deep conceptual issues could be resolved experimentally seemed almost too good to be true, and perhaps not particularly important even if true. Quantum mechanics worked. Why reopen old debates? But gradually, a few researchers began to recognize what Bell had accomplished. He had not merely clarified a philosophical dispute. He had shown that the nature of reality itself was an experimental question. The universe either allowed objects to have independent local properties, or it did not, and this could be determined in a laboratory. By the early 1970s, physicists started designing experiments to test Bell's inequality. The challenge was formidable. Creating entangled particles was difficult. Measuring their properties with sufficient precision and speed was difficult. Ensuring that the measurements were truly independent, that no signal could travel from one detector to the other during the measurement process, was difficult. But the rewards of success would be immense, a direct empirical answer to one of the deepest questions in physics. The experiments would need to close what became known as loopholes, potential escape routes that could allow a local hidden variable theory to mimic quantum predictions despite Bell's theorem. If the detectors were not efficient enough, missing some particles, a local theory might exploit this inefficiency to produce correlations that appeared to violate the inequality. If the measurements were not performed quickly enough or far enough apart, signals traveling at light speed might coordinate the outcomes, preserving locality. Each loophole represented a way that nature could, in principle, be local and real, while still appearing to violate Bell's inequality due to experimental imperfections. Closing these loopholes would require decades of technological refinement and increasingly sophisticated experimental designs. The first convincing tests of Bell's inequality came in the early 1980s, carried out by a French physicist named Alain Aspect and his colleagues. Their laboratory was not extraordinary in appearance, just rooms filled with optical equipment, lasers, detectors, miles of cable connecting instruments to computers that recorded data in streams of numbers. But what happened in those rooms would change how we understand the structure of reality. Aspect's team worked with pairs of photons, particles of light created simultaneously, in a process that entangled them. When a calcium atom was excited and then decayed, it emitted two photons moving in opposite directions, each carrying away part of the atom's angular momentum. These photons were correlated in their polarization, a property describing the orientation of the light wave's oscillation. If you measured the polarization of one photon along a particular axis, quantum mechanics predicted that measuring the other photon along the same axis would yield a correlated result, even though the photons were now separated and traveling apart at the speed of light. The photons passed through polarizing filters, devices that allowed light oriented one way to pass while blocking light oriented another way. By rotating these filters to different angles and recording which photons passed through and which were blocked, the experimenters could measure correlations and compare them to Bell's predictions. The measurements had to be made quickly, before any signal could travel from one detector to the other. The photons had to be separated by enough distance that even light could not cover the gap in the time it took to complete both measurements. This ensured that the choice of measurement angle at one detector could not influence the outcome at the other detector through any local mechanism. The setup was designed to eliminate the possibility of communication between the two sides of the experiment, to close what would later be called the locality loophole. When the data accumulated, the results were clear. The correlations between the photon pairs were stronger than Bell's inequality allowed for any local hidden variable theory. The photons were more tightly connected than they could be if each carried independent predetermined properties. The violations were statistically significant, confirmed through thousands of measurements, far beyond what random chance could explain. Quantum mechanics had predicted these strong correlations, and nature delivered them. The universe, it seemed, was not locally real. Either the photons did not possess definite polarization values before measurement, or measuring one photon somehow affected the other instantaneously across space, or both. The neat classical picture, where objects exist in definite states and influences propagate at finite speeds, could not account for what was observed. Aspect's experiments were not the first to test Bell's inequality, but they were the most rigorous and convinced much of the physics community that the effect was genuine. Earlier experiments had shown suggestive results, but left room for alternative explanations. Aspect improved the design using fast switching mechanisms to change the measurement angles while the photons were in flight, ensuring that the choice of what to measure at one location could not be known at the other location when its measurement occurred. This refinement addressed concerns that some hidden communication between the detectors might be coordinating the results. The experiments were repeated with different configurations, different sources of entangled photons, different detectors. Each time, the same pattern emerged. Bell's inequality was violated. The correlations were too strong to arise from local hidden variables. The implications were profound, but they settled in slowly without fanfare. The results did not make headlines outside the physics community. There were no immediate technological applications, no dramatic demonstrations that would capture public imagination. The discovery was abstract, a confirmation of something quantum mechanics had predicted for decades, but which now carried the weight of direct empirical evidence. It meant that the debate between Einstein and Bohr had been resolved, not through philosophical argument, but through measurement. Bohr had been right in a sense, though perhaps not in the way he thought. Quantum mechanics was not incomplete in the manner Einstein imagined. There were no hidden variables preserving locality and realism beneath the quantum formalism. The strangeness was real, but what did it mean for two particles to be connected in this non-local way? The photons in Aspect's experiments were separated by meters, and later experiments would extend this to kilometers, then hundreds of kilometers. The distance did not matter. The correlation persisted regardless of separation. Measuring the polarization of one photon along a chosen axis instantly determined the outcome of measuring the other photon along the same axis, or produced predictable statistical patterns for measurements along different axes. This was not a signal in the usual sense. You could not use entanglement to send information faster than light, because you could not control which outcome your measurement would produce. When you measured a photon's polarization, you got a result that appeared random. Only when you compared your results with the measurements made on the other photon did the correlation become apparent. That comparison required classical communication, meeting later or sending signals at light speed or slower. So causality was preserved, relativity was not violated in a way that allowed paradoxes. But something deeper was unsettled. The universe revealed itself as fundamentally non-separable. The two photons, once entangled, could not be described as independent objects with their own isolated properties. They remained part of a single quantum system, a whole that could not be decomposed into separate parts without losing something essential. This was not a failure of description. It was the nature of quantum reality itself. Entanglement is difficult to describe without falling into metaphor or mysticism, but it is neither. It is a physical phenomenon with precise mathematical description, confirmed by experiment, yet it resists translation into everyday language because it has no everyday analog. When two particles become entangled, they do not simply influence each other or share information in the way two connected objects might in classical physics. They become aspects of a single quantum state, a unified system that cannot be separated into independent parts. Even when the particles move far apart, separated by distances where no signal could pass between them in the time available, they remain described by a single wave function. That wave function contains all the information about both particles together, but it does not assign definite properties to either particle individually. Before measurement, you cannot say that particle A has this property and particle B has that property. You can only say that the system as a whole has certain definite characteristics, and that when you measure one particle, the outcome will be correlated with what you would find if you measured the other. This is different from classical correlation in a crucial way. If you shuffle two cards, place one in an envelope and send it across the country, and later open your envelope to find the Queen of Hearts, you instantly know the other envelope does not contain the Queen of Hearts. But this correlation exists because the card identities were determined when you placed them in the envelopes. The information was there all along, just unknown to you. Opening one envelope revealed pre-existing information. It did not create it. Quantum entanglement is not like this. When you measure an entangled particle and find a particular outcome, that outcome was not predetermined by hidden information the particle carried with it. Bell's theorem and the experiments that followed demonstrated this conclusively. The measurement genuinely brings a definite value into being from a state that was previously indefinite. And somehow, measuring one particle brings a corresponding definite value into being for the other particle, regardless of the distance between them. The process is not causal in the ordinary sense. Measuring particle A does not send a signal to particle B telling it how to behave. There is no propagation of influence through space, no transmission of information at faster than light speeds. Instead, the measurement of one particle and the correlated outcome at the other particle are both manifestations of the collapse of a single shared quantum state. The two events are connected not by a signal traveling through space, but by their common participation in a quantum whole. When the wave function collapses, it collapses everywhere the entangled system exists, bringing both particles into definite states simultaneously. This simultaneity does not violate relativity because it cannot be used to send messages or establish a preferred reference frame. The outcomes still appear random at each location. Only when the results are compared through communication that respects the light speed limit does the correlation become apparent. Physicists sometimes describe entanglement as a kind of correlation without correlata, a relationship that exists without the relator having independent reality. The particles are not things that have a relationship. They are the relationship, or more precisely, they are nodes in a network of quantum correlations that constitutes the physical state of the system. This language sounds abstract, almost philosophical, but it reflects the mathematics precisely. The wave function of an entangled pair cannot be factored into separate wave functions for each particle. It is irreducibly a description of both together. If you try to describe one particle in isolation, the best you can do is assign it a mixed state, a probabilistic combination of possibilities that reflects your ignorance of which measurement outcome will occur. But this is not ignorance of a pre-existing fact. It is genuine indeterminacy. The particle does not have a definite state on its own. Its state is entangled with the state of its partner. The phenomenon scales in strange ways. You can entangle more than two particles, creating systems where 3, 4, or even thousands of particles share a single quantum state. You can create situations where measuring one particle affects the probabilities of outcomes for many others, all connected through a web of quantum correlations. These multi-particle entangled states are even more remote from classical intuition, exhibiting correlations that have no analog in any theory of independent objects interacting through local forces. And yet, they exist. They can be created, manipulated, and measured in laboratories. They are not theoretical abstractions but physical realities, states of matter that can be prepared and studied with increasing control. The discovery of entanglement's reality did not resolve all questions about what it means or how to interpret it. Physicists still debate the interpretation of quantum mechanics, still disagree about what the wave function represents and what happens during measurement. Some accept the Copenhagen view that the wave function is merely a tool for predicting measurement outcomes, not a description of an underlying reality. Others seek interpretations where the wave function is real, where collapse is an actual physical process, or where all possible outcomes occur in branching parallel realities. These interpretations differ in their metaphysical commitments, but they agree on the empirical predictions, and they all accommodate the reality of entanglement. Whatever you believe about the ultimate nature of quantum mechanics, you must accept that Bell's inequality is violated, that particles separated by vast distances exhibit correlations too strong to arise from local hidden variables, and that the universe is not made of independent objects with predetermined properties waiting to be discovered. After Aspect's experiments, the work continued. The violation of Bell's inequality had been demonstrated convincingly, but science demands replication, refinement, closing every possible alternative explanation. The loopholes remained, technical possibilities that allowed skeptics to argue that perhaps, under very specific circumstances, a local hidden variable theory could still account for the observations. These were not idle objections. They represented genuine gaps in the experimental proof, ways that nature could, in principle, preserve locality while appearing to violate Bell's inequality due to limitations in the apparatus or procedure. Closing these loopholes became a research program that would span decades, requiring advances in technology and increasingly sophisticated experimental designs. One loophole concerned detector efficiency. If the detectors did not register every photon, if some particles escaped detection, then a local theory could exploit this inefficiency. Imagine that the hidden variables not only determined what result a measurement would produce, but also determined whether the particle would be detected at all. A cleverly designed local model could arrange for particles to be detected only when their properties would produce correlations that appeared to violate Bell's inequality, while particles that would reveal the local nature of reality simply went undetected. This sounds contrived, but it was a logical possibility that had to be ruled out. To close the detection loophole, experimenters needed detectors efficient enough that the vast majority of particles were registered so that any bias from selective detection could not account for the observed violations. Another loophole involved the independence of the measurement settings. In aspects experiments and earlier tests, the angles at which polarization was measured were chosen in advance or changed at regular intervals. A local hidden variable theory could, in principle, exploit this if some subtle correlation existed between the hidden variables carried by the particles and the settings chosen by the experimenters. This sounds even more contrived than the detection loophole, requiring a conspiracy between past events that created the particles and future choices made by experimenters. But closing loopholes means eliminating even unlikely alternatives. The solution was to choose measurement settings randomly and rapidly, using quantum random number generators or astronomical observations to ensure that the choices were made independently and could not have been predetermined by any common cause in the particle's past. The locality loophole required that measurements be separated by enough space and performed quickly enough that no signal traveling at light speed could connect them. If the measurement at one location could, in principle, send information to the other location, before the second measurement was completed, then a local theory could account for the correlations through hidden communication rather than pre-existing hidden variables. Early experiments had addressed this by separating detectors by meters and measuring quickly, but perfect closure required careful timing and greater distances. Experiments in the 1990s and 2000s extended the separations to kilometers, using optical fibers to carry entangled photons across cities, ensuring that the measurements were space-like separated, meaning that no signal could connect them without traveling faster than light. Each loophole, when closed, required technological innovation, better detectors, faster switches, more reliable sources of entangled particles, precise timing systems synchronized to nanoseconds. The experiments grew more complex, involving teams of researchers, custom-built equipment, collaborations between institutions. The process was slow, methodical, incremental. Each successful experiment narrowed the space for alternative explanations, but left other loopholes open. A test that closed the locality loophole might still have insufficient detector efficiency. An experiment with highly efficient detectors might not fully address the independence of measurement settings. The goal was to close all significant loopholes simultaneously in a single experiment, leaving no room for a local hidden variable theory to survive. This milestone was achieved in 2015, nearly 5 decades after Bell's theorem and more than 3 decades after Aspect's pioneering work. Multiple research groups around the world performed loophole-free tests of Bell's inequality, using different technologies and approaches, but reaching the same conclusion. One group used entangled photons sent across kilometers of optical fiber in Vienna, with measurement settings determined by quantum random number generators and detectors efficient enough to register nearly every photon. Another group used pairs of entangled ions trapped in separate laboratories, measured with high efficiency and settings chosen using light from distant stars, ensuring that the choices were independent of anything in the particles past light cones. Yet another experiment used entangled photons measured at detectors separated by more than a kilometer, with rapid random switching of measurement angles and high-efficiency detection. All these experiments violated Bell's inequality with overwhelming statistical significance. All of them closed the major loopholes simultaneously. The results were published in prestigious journals, recognized as definitive confirmation of what Aspect and others had shown decades earlier. The universe was not locally real. Objects did not possess independent definite properties before measurement. Measuring one particle could instantaneously correlate with measurements of another, regardless of distance, in a way that no local mechanism could explain. This was not speculation or interpretation. It was established experimental fact, tested and retested under conditions that eliminated alternative explanations. The violation of Bell's inequality was as well confirmed as any result in physics, supported by countless experiments over many decades, using different methods, different particles, different scales of separation. The confirmation did not feel like a revolution. Quantum mechanics had been accepted and used successfully for so long that the experimental proof of non-locality seemed almost redundant, a formalization of what most physicists already believed. But it was more than that. It transformed a philosophical debate into settled science, removed the possibility that some future theory of hidden variables might restore the classical picture, and provided empirical validation for one of the strangest predictions ever made by a physical theory. In October 2022, the Royal Swedish Academy of Sciences announced that the Nobel Prize in Physics would be awarded to 3 scientists: Alain Aspect, John Clauser, and Anton Zeilinger. The citation was precise and understated, noting their contributions to experimental tests of Bell's inequality and pioneering work with entangled photons. But beneath the formal language was an acknowledgement of something more profound. The Nobel Committee was recognizing not just clever experiments or technical achievements, but a transformation in our understanding of what reality is. The prize honored the people who had demonstrated, through decades of careful measurement, that the universe does not conform to the assumptions we inherited from centuries of classical physics. It was a validation of quantum mechanics at its strangest, a confirmation that the features of quantum theory, most troubling to Einstein and his contemporaries, were not artifacts of incomplete understanding, but accurate descriptions of nature. John Clauser had performed some of the earliest tests of Bell's inequality in the 1970s, working with colleagues to create and measure entangled photons years before Aspect refined the technique. His experiments were the first to show clear violations of the inequality, providing initial empirical evidence that local hidden variable theories could not account for quantum correlations. The results were controversial at the time, met with skepticism by some who wondered whether experimental imperfections might explain the findings. But Clauser's work established the feasibility of testing Bell's predictions and opened a path that others would follow, improving techniques and closing loopholes until the evidence became overwhelming. His contribution was foundational, demonstrating that questions about the nature of quantum reality could be addressed experimentally rather than left to philosophical speculation. Aspect's experiments in the early 1980s, as we have seen, refined this approach substantially. He introduced methods for rapidly changing measurement settings while photons were in flight, addressing concerns about hidden communication between detectors. His work convinced much of the physics community that the violations of Bell's inequality were genuine and that local hidden variables were incompatible with observation. The experiments were elegant, combining theoretical insight with experimental precision, and they set a standard that subsequent tests would build upon. Aspect's contributions went beyond the technical. He helped shift the culture of physics, making the study of quantum foundations a respectable and active field rather than a marginal pursuit for those unsatisfied with the pragmatic Copenhagen interpretation. Anton Zeilinger extended this work into new domains, creating increasingly complex entangled states and demonstrating quantum phenomena over greater distances and with more particles. He developed techniques for quantum teleportation, a process where the quantum state of one particle is transferred to another distant particle using entanglement and classical communication. This was not teleportation in the science fiction sense, not the movement of matter or energy through space, but the transfer of quantum information. It required entanglement as a resource and relied on the same non-local correlations that violated Bell's inequality. Zeilinger also pioneered experiments with entangled photons, transmitted through free space over long distances, eventually achieving entanglement between particles separated by hundreds of kilometers, demonstrating that quantum correlations persisted across scales far larger than laboratory benches. His work pushed entanglement from a subtle effect, confirmed in controlled settings, to a robust phenomenon that could be harnessed and applied, laying groundwork for emerging technologies in quantum communication and quantum computing. The Nobel Prize arrived more than 50 years after Bell's theorem and 40 years after the first convincing experimental tests. This delay was not unusual. The prize often recognizes work only after its significance has been fully established and its impact widely appreciated. By 2022, the violation of Bell's inequality was no longer controversial. It was textbook physics, taught to graduate students, incorporated into the foundation of quantum information science. Entanglement had moved from a conceptual puzzle to a practical resource, something that could be created reliably, distributed across networks, and used to perform tasks impossible with classical resources. The Nobel Committee's decision acknowledged this maturation, recognizing that what had once seemed like an esoteric question about the interpretation of quantum mechanics had become central to our understanding of reality and to the technological possibilities of the future. But the prize also represented something deeper. It was an institutional acknowledgement that the universe is fundamentally non-local, that the classical picture of reality as composed of independent objects with predetermined properties is incorrect. This was not a matter of interpretation or philosophy. It was experimental fact, confirmed by countless tests, supported by evidence as strong as any in physics. The three laureates had not discovered entanglement. Quantum mechanics had predicted it decades earlier. But they had proven it was real, that it was not an artifact of the theory's mathematical formalism, but a feature of nature itself. They had turned Einstein's discomfort into a research program, and that program had revealed that Einstein's intuitions, however reasonable they seemed, were wrong about the deep structure of reality. The prize ceremony took place in Stockholm in December, with speeches praising the laureates' persistence and insight. The King of Sweden presented medals and diplomas. The laureates gave lectures explaining their work to audiences of scientists, dignitaries, and students. The rituals were traditional, unchanged for more than a century, a continuity that contrasted with the radical nature of what was being honored. The lectures attempted to convey the significance of the discoveries to non-specialists, explaining how experiments with photons and detectors revealed something fundamental about existence itself. The task was difficult. Entanglement resists simplification, and the violation of Bell's inequality requires understanding assumptions that seem so obvious they are hard to articulate. But the central message was clear. Reality is not what we thought it was, and we know this because we tested it. The Nobel Prize formalized what experiments had been revealing for decades, but accepting the experimental results is different from understanding what they mean. The violation of Bell's inequality tells us that local realism is false, that the universe does not consist of objects with independent predetermined properties, interacting only through local influences. But this negative statement, this list of what reality is not, leaves open the question of what reality actually is. If particles do not have definite properties before measurement, what are they? If measuring one particle instantaneously correlates with another across vast distances without any signal passing between them, what connects them? The mathematics of quantum mechanics provides precise predictions, but it does not offer a simple picture, a visual or intuitive model of what is happening beneath the equations. The difficulty runs deeper than mere complexity. Classical physics, for all its mathematical sophistication, remained tied to intuition. You could visualize forces, trajectories, fields. Even when the calculations became elaborate, the underlying concepts were graspable. A planet orbits because space-time curves around the sun. Light travels as a wave through electromagnetic fields. These descriptions might require abstraction, but they preserved a sense that something definite was happening in space and time, that the mathematics described an underlying physical reality that existed whether we observed it or not. Quantum mechanics breaks this connection. The wave function evolves according to precise rules, but what the wave function represents remains ambiguous. Is it a physical field pervading space? Is it merely a mathematical tool for calculating probabilities? Does it describe reality as it is, or only our knowledge of what we might find when we measure? These questions are not resolved by confirming the violation of Bell's inequality. If anything, the experimental results deepen the puzzle. They tell us that reality cannot be both local and real in the classical sense, but they do not tell us which assumption to abandon or how to replace it. Some interpretations of quantum mechanics reject realism, maintaining that particles simply do not have definite properties before measurement. In this view, the wave function is complete, and asking what a particle is doing when unobserved is meaningless. Measurement brings properties into existence, and the correlations observed in entanglement arise because the act of measuring one particle affects the quantum state that describes both particles together. Other interpretations reject locality in a more explicit way, proposing that the wave function is a real physical field that collapses instantaneously across all space when a measurement occurs, updating the state of the entire system simultaneously. Still, other interpretations, such as the many worlds view, deny that collapse happens at all, suggesting instead that all possible measurement outcomes occur in branching parallel realities. Each interpretation accepts the same experimental facts and makes the same predictions for future measurements. They differ in their metaphysical commitments, in what they claim exists beyond the observable phenomena. This is frustrating for those who want physics to provide a single, clear description of reality. But it may be that quantum mechanics is telling us something even more fundamental, that the questions we are asking presuppose a classical framework that no longer applies. When we ask whether a particle has a definite position before measurement, we are importing concepts from a world where objects are localized and independent. Quantum mechanics suggests that this framework is inadequate, that the universe at its most fundamental level is not made of objects in the classical sense. What is an object if not something with definite properties that exists independently of observation? In everyday experience, this question seems trivial. A table is solid, located in space, possessing mass and dimensions whether anyone measures it or not. But the table is made of atoms, and atoms are made of particles described by quantum mechanics. The solidity, the definite location, the independence, these are emergent features that appear at macroscopic scales due to the interactions of vast numbers of quantum constituents. At the level of individual particles, these features dissolve. A particle is not a tiny solid sphere sitting at a point in space. It is a pattern of correlations, a set of probabilities encoded in a wave function, something that only manifests definite properties in the context of interactions and measurements. This shift from objects to correlations is subtle but profound. It suggests that the fundamental building blocks of reality are not things but relationships. A particle's properties are not intrinsic but relational, defined not by what the particle is in isolation, but by how it interacts with other systems, including measurement apparatus. When two particles are entangled, the relationship between them is more fundamental than the particles themselves. The entangled pair is the primary reality, and the individual particles are abstractions, aspects of that relationship that we extract through measurement. This is why the wave function cannot be factored into separate descriptions of each particle. The whole is not composed of independent parts. The parts are defined by their participation in the whole. This relational view of reality was not entirely new. Philosophers and physicists had explored similar ideas before quantum mechanics emerged, questioning whether objects possess intrinsic properties or whether all properties are relational, defined by connections to other things. But quantum mechanics gives this idea empirical weight. The violation of Bell's inequality is not a philosophical argument. It is observed fact, confirmed by measurement, showing that particles separated by vast distances exhibit correlations that cannot arise from intrinsic properties carried independently by each particle. The correlation is primary. The particles, as separate independent entities, are secondary or perhaps illusory. This does not mean particles do not exist. Electrons are real. Photons are real. You can detect them, count them, use them to carry information and energy. But they are real in a way that differs from classical objects. They are real as nodes in a network of quantum relationships, as carriers of correlations, as aspects of a quantum state that extends beyond any single location. Their reality is contextual, defined by how they relate to other systems, not by intrinsic properties they possess in isolation. The implications extend beyond photons and electrons. Every particle that has ever interacted with another particle becomes, in principle, entangled with it. The interaction creates correlations, and those correlations persist even after the particles separate. The universe is not a collection of isolated billiard balls bouncing off one another and then going their separate ways, each carrying its own independent state. It is a web of quantum correlations, connections that link particles across space and time in ways that have no classical counterpart. Most of these correlations are extremely weak or quickly disrupted by interactions with other particles, which is why we do not notice them in everyday life. But they are there, woven into the structure of the quantum state that describes the universe. This perspective changes what it means for something to exist as a distinct object. In classical physics, an object was defined by its boundaries, by the surface that separated it from the rest of the universe. Inside those boundaries were properties that belonged to the object alone: its mass, its position, its internal structure. The object could interact with its environment, exchanging energy or momentum, but it retained its identity as a separate thing. You could, in principle, specify the complete state of the object without referring to anything outside it. The universe was a collection of such objects, each with its own state, interacting according to laws but fundamentally independent. Quantum mechanics challenges this separability. When a particle interacts with another particle, or with a measuring device, or with the thermal environment around it, the interaction creates entanglement. The quantum state of the particle becomes correlated with the quantum state of the thing it interacted with. You can no longer describe the particle's state without referring to the state of the larger system that includes the particle and its environment. The boundaries blur. The object is no longer fully distinct from its surroundings. Its properties are not intrinsic, but emerge from its relationships with the rest of the universe. This does not mean that objects dissolve entirely into an undifferentiated quantum soup. Practical separability can be maintained when entanglement is weak, or when the correlations average out statistically. A book sitting on a table is entangled with the photons bouncing off its surface, with the air molecules striking it, with the table itself. But these entanglements involve so many particles and so many degrees of freedom that they wash out into classical behavior. The book appears to have a definite position, a definite shape, properties that persist independently of observation. This appearance is not an illusion. It is a real feature of how quantum systems behave when they are large and interacting strongly with their environments. But the appearance is emergent, arising from the statistical behavior of vast numbers of entangled particles, not from the intrinsic nature of some underlying classical substrate. The classical world we inhabit is, in this view, a kind of surface phenomenon, a pattern that emerges from deeper quantum reality. Objects appear distinct because entanglement with the environment forces quantum systems into states that approximate classical behavior, a process called decoherence. When a particle interacts with many particles in its environment, the superpositions that characterize quantum behavior become extremely fragile. The wave function describing the particle and its environment evolves in a way that makes interference effects unobservable, leaving behind only the appearance of definite outcomes. The particle seems to have a definite position, even though it is still fundamentally described by a quantum state that includes correlations with countless environmental degrees of freedom. Decoherence explains why we do not see macroscopic objects in superpositions of different states. Haircat does not appear to be both alive and dead, not because quantum mechanics fails at large scales, but because the cat is constantly interacting with its environment, air molecules, photons, thermal radiation, and these interactions create so much entanglement that the superposition becomes effectively classical. The cat's quantum state is still there, but it is spread across so many degrees of freedom, entangled with so much of the environment, that recovering the quantum coherence would be impossible in practice. What remains observable is a classical approximation, an object that appears to have definite properties because the quantum correlations are hidden in the complexity of the environment. This does not solve the measurement problem, or explain why measurement produces a single definite outcome rather than a superposition. Decoherence explains why we do not see interference effects in everyday life, why the quantum world appears classical at macroscopic scales, but it does not tell us what happens to the other branches of the wave function, the possibilities that do not manifest. Different interpretations answer this differently. What decoherence does make clear is that the boundary between quantum and classical is not sharp or fundamental. It is a question of scale, complexity, and the strength of interactions with the environment. The shift from objects to relationships, from intrinsic properties to correlations, alters how we think about identity and persistence over time. In classical physics, an object maintains its identity by continuously existing in a definite state, evolving smoothly from one moment to the next according to deterministic laws. In quantum mechanics, identity is more subtle. A particle's state is defined by its place in a network of correlations, and that network evolves according to quantum rules that include superposition and entanglement. What persists is not a set of intrinsic properties but a pattern of relationships that links the particle to the rest of the universe. The relational nature of quantum reality becomes particularly clear when thinking about information rather than matter. Classical information is straightforward. A bit is either 0 or 1, a coin shows either heads or tails, a message contains symbols that have definite values, whether anyone reads them or not. The information exists independently, encoded in the physical state of some medium. A book contains information in the arrangement of ink on paper, and that information persists unchanged until something alters the physical substrate. Information can be copied perfectly. You can read a number from one place and write it to another, creating two identical copies without disturbing either. The original and the copy are independent, carrying the same information but existing as separate physical systems. Quantum information behaves differently. A quantum bit, or qubit, can exist in a superposition of 0 and 1, a state that is neither fully one nor the other until measured. This superposition is not ignorance of a definite classical value. It is a genuinely quantum state, something that has no classical analog. When you measure the qubit, you get either 0 or 1, but the measurement changes the state, collapsing the superposition into a definite outcome. You cannot read quantum information without disturbing it, and you cannot copy quantum information perfectly. There is a theorem, the no-cloning theorem, that proves it is impossible to create an identical copy of an unknown quantum state. The process of attempting to copy would necessarily disturb the original, or produce an imperfect duplicate. Quantum information cannot be duplicated in the way classical information can. Entanglement is a form of quantum information, a correlation between particles that cannot be created by exchanging classical signals. When two qubits are entangled, measuring one provides information about what you will find when measuring the other. But this correlation is encoded in the shared quantum state, not in the individual states of each qubit separately. The information is relational, existing in the connection between the qubits rather than in either qubit alone. This has practical consequences. Entangled qubits can be used to perform tasks impossible with classical resources, such as quantum teleportation or certain quantum computing algorithms. They represent a resource, something that can be created, distributed, and consumed in protocols that manipulate quantum information. But calling entanglement a resource, while useful for understanding its applications, also risks obscuring its deeper strangeness. A resource is something you possess and use, something that exists independently as a stock you can draw upon. Entanglement is not like this. It is not a substance or a field or a property localized in one place. It is a feature of how two or more systems are correlated, a non-local aspect of their shared quantum state. When you use entanglement in a quantum protocol, you are not consuming something stored locally. You are exploiting a relationship that spans the separation between particles, a connection that cannot be accounted for by classical means. This becomes vivid in quantum teleportation. Despite the name, nothing physical moves from one location to another. Instead, the quantum state of one particle is transferred to another distant particle using entanglement and classical communication. The process requires that the two locations share an entangled pair in advance. When the sender performs a measurement on the particle whose state is to be teleported and one member of the entangled pair, the result is communicated classically to the receiver. The receiver then performs an operation on their member of the entangled pair, transforming its state into a copy of the original. The original particle's state is destroyed in the process, preserving the no-cloning theorem. What has happened is a transfer of quantum information, accomplished by exploiting the correlations present in the entangled pair. The procedure sounds artificial, a clever trick rather than a fundamental insight. But it reveals something essential about quantum mechanics. The quantum state is not a property of matter in the way mass or charge is a property. It is information, a description of correlations and probabilities, something that can be transferred from one physical system to another without moving particles or energy. The quantum state is the reality, and the particles are carriers of that state, substrates that can be reconfigured to encode different information. This inversion, where information is primary and matter secondary, fits the relational view emerging from Bell's theorem and entanglement experiments. If reality is fundamentally about correlations rather than intrinsic properties, then quantum information, the mathematical description of those correlations, is as close as we can come to describing what exists. This does not mean the universe is made of mathematics, or that reality is somehow less than physical. The quantum state describes something real, the outcomes that will be observed when measurements are made, the patterns that persist across time and space, the constraints that govern how systems behave. But it describes reality in a way that differs from classical physics. Instead of objects with intrinsic properties evolving in space and time, we have quantum states encoding correlations, evolving according to unitary dynamics, occasionally collapsing when interactions or measurements bring definite outcomes into being. The language shifts from things to processes, from being to becoming, from substance to structure. This structural view is not merely abstract. It grounds the emerging field of quantum information science, which treats quantum systems as carriers of information and develops technologies based on manipulating quantum states. Quantum computers exploit superposition and entanglement to perform calculations that would be infeasible classically. Quantum cryptography uses the no-cloning theorem and the disturbance caused by measurement to create communication channels whose security is guaranteed by the laws of physics rather than by computational complexity. These technologies are not science fiction. They exist in laboratories, advancing steadily from proof-of-concept demonstrations toward practical applications. Their success depends on the same quantum features that violate Bell's inequality, the same non-local correlations that troubled Einstein, now harnessed as resources for computation and communication. The question of what measurement is and what role the observer plays has haunted quantum mechanics since its inception. The mathematics describes how the wave function evolves smoothly and deterministically when a system is left undisturbed, spreading and interfering according to the Schrödinger equation. But it also describes something discontinuous and probabilistic, the collapse that occurs when a measurement is made, transforming a superposition of possibilities into a single definite outcome. This collapse is not part of the smooth unitary evolution. It is an additional postulate, something imposed on the theory to account for the fact that measurements yield definite results rather than superpositions. The contrast between these two modes of evolution, smooth and deterministic versus abrupt and probabilistic, is the measurement problem, one of the deepest puzzles in the interpretation of quantum mechanics. What counts as a measurement? In the laboratory, A measurement involves an apparatus, a detector that registers photons, a screen that shows where particles arrive, an instrument that displays a number. These devices are macroscopic, made of vast numbers of atoms, and they interact with the quantum system being measured. The interaction entangles the measuring device with the system, correlating the device's state with the system's state. If the particle is in a superposition of two positions, and a detector sensitive to position interacts with it, the combined system enters a state where the detector's pointer is in a superposition of two readings, each correlated with one of the particle's positions. But we never observe detectors in superpositions. We see the pointer in one definite location, indicating one definite outcome. The Copenhagen interpretation attributed this transition from superposition to definite outcome to the act of observation itself, suggesting that measurement causes the wave function to collapse. This worked as a practical rule for making predictions, but it introduced an uncomfortable dualism into physics. On one side, quantum systems evolving smoothly according to deterministic equations. On the other side, observers and measuring devices that somehow stood outside this evolution, causing collapses when they interacted with quantum systems. Where was the boundary? At what point did a physical interaction become a measurement? Did it require a conscious observer, or was any macroscopic device sufficient? The theory provided no clear answer, leaving the boundary between quantum and classical vague and subjective. Some interpretations sought to eliminate this boundary by denying that collapse happens at all. In the many worlds interpretation, the wave function never collapses. Instead, when a measurement occurs, the universe branches into multiple versions, one for each possible outcome. Each branch contains an observer who sees a definite result, but all outcomes occur, each in its own separate branch of reality. This preserves determinism and removes the special role of observation, but at the cost of accepting an enormous proliferation of parallel universes, most of which are forever inaccessible to us. The interpretation is elegant in its commitment to the wave function as the complete description of reality, but it raises questions about probability and the nature of existence that remain unresolved. Other interpretations propose modifications to quantum mechanics that make collapse a real physical process, governed by new equations that include stochastic elements or gravitational effects. These approaches preserve a single outcome while avoiding the special role of the observer. But they introduce new physics beyond standard quantum mechanics, physics that has not yet been confirmed experimentally. Still other interpretations, like Bohmian mechanics, restore determinism by positing that particles do have definite positions at all times, guided by a pilot wave that evolves according to the Schrödinger equation. This reproduces the predictions of quantum mechanics while providing a clear ontology, but it requires accepting non-locality explicitly, with the pilot wave instantaneously influencing particles across space. What all these interpretations share is an acknowledgement that measurement is a physical interaction, not a mystical process requiring consciousness. The observer is not special in any metaphysical sense. A human looking at a detector does not cause collapse differently than a camera recording the result or a rock being struck by a particle. What matters is the interaction between the quantum system and something macroscopic, something with many degrees of freedom that become entangled with the system. This entanglement, combined with decoherence from interactions with the environment, produces the appearance of definite outcomes from an observer's perspective, whether that observer is a person, a machine, or any physical system capable of registering information. Decoherence helps clarify why measurements produce definite results without invoking collapse as a separate process. When a quantum system interacts with a macroscopic measuring device and both interact with the surrounding environment, the delicate phase relationships that characterize superpositions are rapidly destroyed. The system and device become entangled with so many environmental degrees of freedom that interference effects become unobservable. From the perspective of any subsystem, including an observer, the quantum state appears to have collapsed into one branch, even though the full wave function still contains all possibilities spread across the environment. The observer does not see a superposition because the correlations that would reveal it are hidden in environmental degrees of freedom that cannot be accessed. This does not fully solve the measurement problem, because it does not explain why a particular outcome is observed rather than another, or what happens to the unobserved branches. But it removes the need for a special collapse mechanism triggered by observation. The appearance of collapse emerges naturally from the dynamics of entanglement and decoherence, from the way quantum systems interact with complex environments. The observer's role is not to create reality, but to become correlated with it, to join the web of entanglements that constitutes the physical state of the universe. We live in a quantum universe, surrounded by quantum phenomena, even though our daily experience appears thoroughly classical. The chair you sit on, the air you breathe, the light entering your eyes, all of these are quantum systems, composed of particles whose behavior is governed by wave functions and superpositions. Yet none of them seem strange or probabilistic. They appear solid, definite, predictable. The quantum nature is hidden, not because it is absent, but because it manifests at scales and in contexts where its effects average out or become practically unobservable. The classical world is not a separate domain where different laws apply. It is the quantum world viewed through the lens of large numbers and strong environmental interactions, a regime where quantum mechanics produces behavior that approximates the classical physics we learned first. The transition is gradual and context-dependent rather than sharp. There is no specific size or complexity at which quantum mechanics stops and classical physics begins. A single atom is quantum, exhibiting superposition and interference. A million atoms are still quantum, though maintaining coherence becomes increasingly difficult. A grain of dust contains trillions of atoms, and while its quantum state is extraordinarily complex, entangled with countless environmental degrees of freedom, it is still in principle described by quantum mechanics. The classical appearance arises from the practical impossibility of isolating the grain from its environment and observing quantum interference across such a vast system. The quantum effects are there, but they are washed out, hidden in the noise of environmental interactions that decohere superpositions faster than they can be observed. Remarkably, there are systems where quantum effects persist at scales visible to the naked eye. Superconductors are macroscopic objects, sometimes centimeters or meters in size, where electrons pair up and move in a collective quantum state that extends throughout the material. This state exhibits zero electrical resistance, allowing currents to flow indefinitely without energy loss. The phenomenon is fundamentally quantum, arising from coherence maintained across vast numbers of particles. Similarly, superfluids are liquids that flow without viscosity, climbing up the walls of containers and exhibiting other behaviors that have no classical explanation. These are not microscopic curiosities. They are bulk materials behaving quantum mechanically because their internal structure and low temperature allow quantum coherence to survive at macroscopic scales. Even more striking are recent experiments demonstrating quantum interference with large molecules containing hundreds or even thousands of atoms. These molecules are sent through double-slit apparatuses, and they produce interference patterns, showing that they too can exist in superpositions of passing through both slits simultaneously. The molecules are not point particles. They have complex internal structures, vibrating and rotating in ways that couple to the environment. Maintaining coherence long enough to observe interference requires extraordinary experimental care, isolating the molecules from air molecules and thermal radiation that would decohere the superposition. But it can be done, and it has been done, pushing the boundary of observable quantum behavior to larger and larger systems. The experiments suggest that quantum mechanics does not fail at any particular scale. The challenge is not a breakdown of the theory, but the practical difficulty of isolating systems from their environments. In principle, a human being is a quantum system, described by an enormously complicated wave function encoding the positions and momenta of every particle in the body. In practice, this wave function is so entangled with the environment, and the environment is so complex and uncontrollable that quantum coherence is destroyed almost instantly. The person appears classical because decoherence is extremely rapid and thorough, not because quantum mechanics ceases to apply. This raises a subtle question. If everything is quantum, and the classical world is merely an appearance arising from decoherence, does quantum mechanics apply to the universe as a whole? The universe has no external environment to decohere it. There is nothing outside the universe to become entangled with, no measuring apparatus that stands apart from the system being measured. The wave function of the universe, if such a thing exists, must evolve according to the Schrödinger equation without collapse, because there is nothing external to cause collapse. This perspective leads to interpretations like many worlds, where the universe is a vast superposition of all possible configurations, and observers within the universe experience definite outcomes because they are part of branches that have decohered from each other through internal interactions. Alternatively, one might argue that the universe does not have a wave function in the same way a particle or a small system does, that quantum mechanics applies to subsystems but not to the totality of existence. The question touches on the interface between quantum mechanics and cosmology, an area where our understanding remains incomplete. We have quantum field theory, which extends quantum mechanics to account for the creation and annihilation of particles and the dynamics of fields. We have general relativity, which describes gravity and the large-scale structure of spacetime. But we do not have a fully developed theory of quantum gravity, a framework that unifies quantum mechanics with the curved spacetime of general relativity. The search for such a theory is ongoing, with approaches like string theory and loop quantum gravity proposing different mathematical structures that might underlie both quantum mechanics and gravity. These foundational questions remain open, but they do not undermine the empirical success of quantum mechanics within its domain. For systems that can be isolated well enough to observe quantum effects, the theory makes predictions of extraordinary precision, confirmed by countless experiments. For macroscopic systems where decoherence is rapid and thorough, quantum mechanics reduces to classical physics in the appropriate limit, explaining why the everyday world appears the way it does, while retaining quantum mechanics as the fundamental description. The discovery that reality is not locally deterministic changes more than physics. It alters the relationship between observer and world, between knowledge and existence, between the certainty we thought we possessed and the irreducible strangeness that experiments reveal. For centuries, the project of science was to uncover the mechanisms beneath appearances, to find the hidden gears and pulleys that made the universe run. Each discovery peeled back a layer of mystery, revealing order and predictability underneath. The planets moved in ellipses because gravity shaped space-time. Light traveled in waves because electric and magnetic fields oscillated together. Every why had an answer, and that answer pointed to something definite, something that existed whether we looked at it or not. The universe was a puzzle, intricate and vast but ultimately solvable. We were cartographers mapping a landscape that existed independently of our maps. Quantum mechanics does not fit this picture. It tells us that certain questions have no answers, not because we lack information, but because the questions assume a reality that does not exist. Asking where an electron is when you are not measuring it is like asking what direction is north of the North Pole. The question carries assumptions that break down when examined closely. The electron does not have a position in the classical sense until position is measured. Before that, it exists in a state described by probabilities, by a wave function that encodes all possible positions weighted by their likelihood. The wave function is not ignorance, it is the reality. And when you measure, you do not reveal a pre-existing fact. You participate in bringing a definite outcome into being from a field of possibilities. This participation is not mystical. It does not require consciousness or intention. A detector measuring the electron is a physical interaction, an entanglement of the detector's state with the electron's state, followed by decoherence as the environment becomes involved. But the interaction is necessary. The definite outcome does not exist beforehand, waiting to be discovered. It emerges through the measurement process. The observer and the observed are not separate in the way classical physics assumed. They are entangled, correlated, parts of a single quantum system whose state cannot be factored into independent descriptions. This means that knowledge is not simply a matter of uncovering what is already there. It is relational, arising from interactions between the knower and the known. You cannot observe the universe from outside, as if it were an object laid out for inspection. You are part of the universe, entangled with it, and your observations are interactions that shape what becomes definite. This does not mean you create reality in an arbitrary way. The quantum state constrains what outcomes are possible and assigns probabilities to each. You cannot choose what you will find when you measure, but the measurement is not passive. It is an active participation in the unfolding of events, a moment where possibilities collapse into actuality through your interaction with the system. Living with this knowledge requires a shift in perspective. The classical worldview offered certainty and separation. Objects existed independently, with definite properties following deterministic laws. You could, in principle, know everything about the present and calculate the future with perfect accuracy. The universe was mechanical, predictable, indifferent to observation. This was both comforting and isolating. Comforting because it suggested the world was orderly and comprehensible. Isolating because it placed the observer outside the system, looking in from a position of detachment, never truly connected to the phenomena being studied. The quantum worldview replaces certainty with probability and separation with entanglement. You cannot know everything, even in principle, because some properties do not exist until measured. You cannot predict individual outcomes with certainty, only probabilities. And you are not separate from what you observe. You are entangled with it, part of a network of correlations that extends throughout the universe. This is less comforting in some ways. It removes the illusion of complete control, the hope that everything can be predicted and understood through sufficient effort. But it is also less isolating. It suggests that connection is fundamental, that the universe is not a collection of separate objects, but a web of relationships, and that you are woven into that web as an integral part, not an external observer. The violation of Bell's inequality makes this concrete. Two particles separated by kilometers or light years remain connected through entanglement. Measuring one affects the probabilities of outcomes for the other, not through any signal, but through the collapse of their shared quantum state. This non-local connection is a feature of reality itself, confirmed by experiment, undeniable. It means that separation is not absolute. Distance does not sever the correlations created when particles interact. The universe is more unified, more interconnected than classical physics allowed us to imagine. This does not erase individuality or make everything blend into an undifferentiated whole. Objects still exist, with properties that can be measured and described, but their existence is relational, defined by their place in a network of quantum correlations rather than by intrinsic properties they possess in isolation. A particle is what it is because of how it relates to other particles, to fields, to the observer who measures it. This relationality is not a deficiency or incompleteness. It is the nature of reality at its most fundamental level. We return in the end to the simplest things: a chair in a room, a coin resting on a table, the moon moving through darkness overhead. These objects seemed so obvious once, so solid in their independence, existing whether we looked at them or not. That assumption was not wrong in any practical sense. The chair does not vanish when you leave the room. The moon continues its orbit. But the certainty beneath these observations, the philosophical foundation that said objects possess definite properties independent of measurement, has been quietly withdrawn by experiment. The universe is not what we thought it was, not because we were naive or unscientific, but because reality at its deepest level operates by principles that have no equivalent in everyday experience. Objects are not separate in the way they appear. Particles separated by vast distances remain connected through correlations that cannot be explained by anything traveling between them. Properties do not exist before measurement in the way classical physics assumed. The act of observation participates in bringing definiteness into being, not through any magic or consciousness, but through physical interaction, through entanglement and decoherence, through the relational structure of quantum mechanics itself. This is not a metaphor. It is measured fact, confirmed across decades, across laboratories, across different particles and different scales. The Nobel Prize in 2022 formalized what experiments had been revealing since the 1980s. Bell's inequality is violated. Local hidden variables cannot account for quantum correlations, and reality is fundamentally non-local and relational. The universe does not consist of independent objects with predetermined properties. It consists of correlations, relationships, entanglements that persist across space and define what becomes real when measurements occur. What remains is a kind of strangeness that will not resolve. No matter how familiar the mathematics becomes, no matter how precisely we can predict quantum phenomena, the underlying picture resists intuition. We cannot visualize superposition or entanglement in the way we can visualize orbits or waves. We cannot translate quantum mechanics into a simple story about things moving through space and time. The theory works perfectly and precisely, but it describes a world that is deeper and stranger than the one we perceive. Perhaps this is what the discovery means. Not that the universe is incomprehensible, but that comprehension requires letting go of assumptions we did not know we were making. The classical picture felt natural because it matched our direct experience, the world of medium-sized objects moving at moderate speeds. But that world is a special case, an emergent approximation of quantum reality shaped by decoherence and large numbers. Beneath it lies something more fundamental, a web of correlations, a relational structure where properties are contextual, where separation is not absolute, where observation and reality are intertwined in ways that preserve no clear boundary between knower and known. We live in this reality. We are made of it, entangled with it, part of the network of quantum correlations that extends throughout space and time. The chair exists, the moon orbits, but their existence is not the simple independent persistence we once imagined. It is something more subtle, more interconnected, bound up with relationships that stretch across the universe and only become definite through interaction. The experiments have spoken, the data has accumulated, the loopholes have been closed. What began as Einstein's discomfort, as a thought experiment meant to show quantum mechanics was incomplete, became a research program that revealed the opposite. Nature is more quantum than even the architects of the theory fully anticipated. Reality is relational. Separation is not fundamental, and the universe in its deepest structure is a unity we are only beginning to understand. If this journey brought you a sense of calm, you can subscribe to Quiet Science and continue exploring these silent depths with us.